Okay, so we've been working on the study of reactor design, and we've been focusing on how when we do reactor design, what we're actually doing is we have some chemical reaction that exhibits some kinetics, and we want to design a reactor around those kinetics. And one of the important properties that we've been looking at is the conversion. So if I have some reaction and I want to convert some amount of the reactant into product, how can I design a reactor to do that? So we saw, for example, in the Levenspiel lecture, how we could choose a CSTR versus a PFR reactor in order to carry out the reaction to some certain conversion. We then saw how to write rate laws. In this lecture, we're going to learn how to turn a rate law that's a function of concentration into a function of conversion. And the concentration component of the rate law has two pieces. It has the mole term in the numerator, and it has the volume term in the denominator. We're going to see in this lecture how to convert both of those into functions of conversion. So in this lecture, we'll write the concentration in terms of conversion. So if we think about concentration, it has two forms. In a flow reactor, we say it's equal to, so Ci, concentration of species I, is equal to the molar flow rate of I divided by the volumetric flow rate. And so recall that this script V is volumetric flow rate. And in a batch reactor, we don't work in terms of flow, we work in terms of number of moles, and we denote that with capital N. So the concentration is equal to Ni, and in this case, over V. So concentration is equal to the moles present divided by the volume. And conversion can influence all of these terms. So first, let's recall the influence that conversion has on the mole terms, so the molar flow rate and the number of moles. So to do that, let's consider some chemical reactors. So we'll look at a batch reactor. I'm going to draw that over here. And this is carrying out some reaction. So we'll say it's carrying out the reaction AA plus BB goes to CC plus DD, where the lowercase letters are the stoichiometric coefficients. And so this will be a liquid phase reaction. And in this container, we have A, B, C, and D. We'll say at time equals 0, then Na equals Na0, and B equals NB0, and C equals NC0, and ND equals ND0. And at time equals T, so we allow the reaction to proceed. So the reaction has been carried out. For some time. Then at that time we have Na equals Na, Nb equals Nb, Nc equals Nc, and Nd equals Nd. And I could say that all of those are evaluated at time t, but for simplicity, I'm just going to say, for example, Na is equal to Na. So that's my batch reactor. Similarly for a flow reactor, so I can draw a flow reactor, arrows to denote there's flow. And I would say coming into my reactor, I have FA naught, I have FB naught, I have FC naught. And then coming out, I have FA, FB, FC, and FD. And if I wanted to make sure that I know these are reactors, I can draw stirs. So let's say that species A is the limiting reactant. That means we can solve the mole balances for these reactors in terms of the conversion of A. And so we saw how to do that. So we would say XA is equal to So we know how to write the molar amount of A in terms of the conversion and the initial amount. So we could rearrange this equation to solve for this term or this term, and we know how to do that. We can also write the molar amounts or the molar flow rates of the other species in terms of XA. So let's do that. So for the batch reactor, and the number of moles of species A is equal to the amount initially, and I'm not, minus the ratio of stoichiometric coefficients, I, divided by the stoichiometric coefficient of the limiting reactant, times the amount present initially of the limiting reactant, times the conversion of the limiting reactant. And similarly, we can write an equation for the flow reactor. So you may wonder why this is a minus sign. So recall that stoichiometric coefficients are negative when the species is a reactant, and it's positive when the species is a product. So if species I is a reactant, then it's going to have the same sign as species A, and so this term is going to be positive. So then this term in the parentheses is going to be positive. So then this entire term will be negative. So that makes sense. So the amount at time t is going to be less than the amount initially. Similarly, if species I is a product, then that means that the term inside the parentheses is going to be negative. So you'd be subtracting a negative value. So you'd be adding this quantity to your amount initially. So you'd be generating the species if it were a product. So that makes sense. So let's make a note of that. So we can say, if we look at our stoichiometric ratios, stoichiometric coefficients are negative and positive for products. And I'm going to say recall, because we brought this up in a prior lecture. So this is how we account for the molar amount and the molar flow rate of different species. For example, if we were looking at a flow reactor and we wanted to look at species B, then what we would say is FB is equal to FB naught minus the stoichiometric coefficient of B over the stoichiometric coefficient of A. So that would be negative lowercase b divided by negative lowercase a times the flow rate, the initial flow rate of A times the conversion of A. And that's how we would account for the molar flow rate of B across the reactor. So you may remember these formulas may look familiar to you. They are the exact formulas that we used in the material and energy balance course when we did the extent of reaction method. Okay, so for more on that, on how to write a flow rate or a molar amount of a species in terms of the conversion of the limiting reactant when that species is not the limiting reactant, you can see tables 4.1 and 4.3 in Fogler. There's also a video in today's module that shows how to construct a stoichiometric table. So a stoichiometric table is a good way, as you're starting out learning these concepts, to keep track of the flow rates of the different, or the flow rates of the molar amounts of the different species. So I suggest that you either watch this video or there's an example problem in Fogler that will illustrate this in more detail. So if I take these formulas and I rearrange them, I get on this side Ni is equal to this quantity here, and also here. This has a specific definition. So this is theta I, and this is the capital Greek letter theta I, is equal to NiO over NaO, or FiO over FaO, where A is the limiting reactant. We can abbreviate that LR. So this is an important quantity or definition, this theta I, the moles of species I initially, or the moles of species I fed, divided by the moles of the limiting reactant initially, or the moles of the limiting reactant that's fed. So you'll see this definition used in the textbook, for example. Where this becomes nice is when we have multiple equations that contribute to our design equation. So maybe we have multiple reactions, or maybe we have multiple reactions and an energy balance. And when we do that, you'll see in a future lecture, it becomes convenient to let the computer do all of the solving for us. So we want to just write out symbolic equations and then feed values to the variables or the parameters in the equations, and let the computer do the solving. Because of that, we can simply write out this definition for each component. Theta I is equal to whatever this is divided by whatever this is, and then we can write out a consistent formula for everything. That makes it a little bit easier to check our work. So to fully have these formulas, you would take this theta term and substitute it in there. So the final formulas are those written here. So some important notes. We can always write the conversion for any of the reactant species. So it doesn't matter if they're the limiting reactant or not. In the last example, we said that A was the limiting reactant, and we can of course write the conversion of A. We could additionally write a conversion of B, and that tells us how much of those species has reacted. However, if we want to solve a reactor design equation, a mole balance in terms of conversion, we must use the limiting reactant. We discussed this before, but if we're not using the limiting reactant, then that causes the reaction to proceed farther than it can. So the reaction can only proceed until the limiting reactant has been reacted away. If we are writing a mole balance in terms of the conversion of a non-limiting reactant, then we could react completely away the limiting reactant, but the reaction would still be allowed to proceed. So that's, of course, not physical. So always make sure that when you write your problem in terms of conversion, you are writing in terms of the conversion of the limiting reactant. In this class, so in the book and in the notes, you're going to see that we are almost always writing everything in terms of species A. However, species A isn't always the limiting reactant, so make sure that you're checking to make sure what the limiting reactant is before you write your balances.